Good afternoon, everybody, or good morning, everybody. Today we're going to do Chapter 8, Section 4, Trigonometric Substitutions. Trigonometric substitutions occur when we replace a variable of integration by a trig function. In other words, if we're integrating with x, we can transfer or substitute x for the function a times tangent x. I'm sorry about that. So it's replacing the variable of integration with a trig function. So for example, instead of x, we could do a side a times tangent the angle theta, or x equals a sine theta. These are the most common ones. And what these relate to is in the example sheet I gave you all. These substitutions are effective in transforming integrals involving these type of integrals into these type of functions. So, and that's what we're going to look at. We're going to be looking for, when we do these transformations, we're going to be looking for a function that's looks like this, and like this. Now, what these all relate to are so we have our angle theta, this is length x, this is side A. So to find the hypotenuse, it's Pythagorean theorem, so it's a squared plus x squared. If x is here, and that's our hypotenuse, then to find this, again, using the Pythagorean theorem, that's Pythagorean. So this side here will be square root of a squared minus x squared. Remember, this plus this equals the square of this equals the square of that. And lastly, we have this, where, again, these are angles theta. So if this is our x, then this is our adjacent side. Then we're looking at x squared minus a squared. So now how do these relate to those? We'll use this when we transform to the tangent function. We'll use this one when we do the sine function of theta. And then this one is the secant function. So what we're looking at here is, instead of our x function, x, we're going to use a squared plus x squared. That equals a, since this can never be negative, we have to take the absolute value of the tangent. And this one, instead of x, we'll use the square root of a squared minus x squared. That equals to a, again, we have to use the absolute value because this value can never be negative. And then the square root of x squared minus a squared equals a absolute value of secant theta. So these are the type of transformations we're going to make. All right. So we'll be looking for how it's set up in our equation. So also, with our function x equals a tangent, so we had originally a squared plus x squared. And we get that. Okay, for our tangent function, so we're looking at here, just look inside that. So we have a squared plus x squared. So we have a squared. X is that x. So that becomes a tangent theta squared, which becomes a squared plus a squared tangent squared theta. We can factor out the a squared. So we have 1 plus tangent squared theta. One plus tangent is the same thing as the secant squared theta. Because cosine squared plus sine squared equals 1 theta. So if we divide everybody by cosine, I get 1 plus sine over cosine is tangent. 1 over cosine is secant squared. So it comes from identity that way. With x equals a sine theta, which becomes a squared minus x squared, which is a squared minus a sine theta squared. Sine squared. So we can take out the a squared, so we have 1 minus sine squared is equal to cosine squared. Again, cosine squared theta plus sine squared theta equals 1. Move the sine squared. Use identities. So using identities, we're going to rewrite these. And then with x equals a secant theta, we get x squared minus a squared. So it's x squared minus a squared equals a secant theta squared minus a squared. We can factor out an a squared, which gives us secant squared minus 1. Secant squared minus 1. Move the 1 over there. It gives us tangent squared. All right, so those are how we can use transformations and identities to get other functions. These also apply to when we have inverse functions. For example, the first one we have is x equals a tangent theta. Solving for tangent, we divide both sides by a. So we get x over a equals tangent theta. The inverse of tangent of x over a, inverse tangent of tangent theta, these cancel, they're inverses of each other. So theta equals the inverse tangent of x over a, where theta is between, since it's tangent, negative pi over 2 and pi over 2. And we can do it to all three of them. So x equals a sine theta divided by a. So we have x over a equals sine theta. Take the inverse sine of both sides. Those cancel, so we have theta equals inverse sine of x over a, with our theta being there. The same thing is true for our secant. So x over a equals secant theta. So there's, and this one's, we have two parts. If x over a is greater than or equal to 1, then we're between 0 pi over 2. If x over a is less than or equal to -1, then we're just the opposite side. Ooh. Because they have to overlap that point. All right, so let's see what we have here. Let's get to our first example. Cool. I gave you all also the procedures of finding these things. So here are the procedures from your sheet. Write down the substitution of x, calculate the differential dx, and specify the selected value theta for the substitution. Substitute the trigonometric expression and the calculated differential into the integrand, and then simplify the results algebraically. These are the procedures to substitute. Integrate the trigonometric integral, keeping in mind the restrictions on the angle theta. Draw an approximate reference triangle and to reverse the substitution. Let's see what all that stuff means. All right. So the first one. Evaluate the integral of dx over radical x 4x plus x squared. Example 1. The integral, the open integral, dx 4 plus x squared. Now, looking at our sheet earlier, which one deals with this one? We have to be aware that this has to be a perfect square. So we have 2 squared plus x squared. So our a equals 2. So which equation do we have that a squared plus x squared? A squared plus x squared. That equals x equals tangent. So we know here's a solution. So a is equal to 2. And 4 plus x squared equals 2 squared plus x squared. Then we use the a tangent theta. Since a is 2, we have 2 tangent theta. Now we have to find the derivative. Choose a derivative of tangent. is secant squared theta, d theta. And from our graphs we talked about, our domain will be negative pi over 2 to pi over 2. So as we had earlier, we had a squared plus x squared, which in our case is 2 squared plus x squared, which is equal to 4 plus x squared. X is tangent 2 tangent theta squared, which is 4 plus 4 tangent squared theta. So we take away a 4, we have 1 plus tangent squared theta. 1 plus tangent squared theta is secant squared theta. All right. So that's the first one. We know what that is now. Because that's what goes in, that's what takes place of the inside the radical. So we're going to have 4 secant squared theta. The reason we do that now, because it's much easier, we can now we get 2 secant theta. So our equation dx over square root of 4 plus x squared can be written, because this becomes 4 secant squared theta, and our dx is up there. So it's 2 secant squared theta d theta. Two secant squared theta d theta over 4 becomes 2 secant theta. The 2's cancel. So we're looking at the integral of secant theta d theta. The integral of secant is ln absolute secant theta plus tangent theta plus c, since it's an open interval. Right, as the instruction said, we have to reverse back to our original functions. So now we have to take the secant and tangent part and put it back into our terms of 4 and x squared. So we know originally, know that x is equal to 2 tangent theta. And we know that the square root of 4 plus x squared is equal to the square root of, no, it's just 2 secant, or that equals to 2 secant theta from here. Because all of this came from here. All right, so I got to change ln secant theta plus tangent theta plus c back in our normal terms. So secant is 4 plus x squared over 2. That's secant. And tangent is x over 2. For whatever value x we're given. All right, let's look at example 2. Example 2. Here we find an expression for the inverse hyperbolic sine function in terms of the natural logarithm. Following the same procedures in example 1, we find that example 2. Evaluate. So we know that dx a squared plus x squared is equal to the integral of secant theta, d theta, where x is equal to a tangent theta, dx is equal to a secant squared theta, d theta. We'll have more problems than that. So what we did earlier, the same, actually follows the same logic. Dx is the same thing we had here from that. So the dx is that. So we have the integral of a secant squared theta d theta. And then we had the square root, which made it a secant theta, which then took us to the ln of secant theta plus tangent theta plus c, because the a's cancel, one of the secants cancel, so we had the integral of secant theta. And that's what we did last time. And that's what we did last time. And then from here, from the secant function, we found it was square root of a squared plus x squared over a, and tangent was x over a. All right, so in this one, I'm saying, find how, here we find the expression of the inverse hyperbolic sine. So we're looking at how it relates to the inverse hyperbolic function of x over a, because we're looking for the angle. And that's what d theta, this is the angle we're looking at. Because remember, inverse functions, this is not the, this, if we had sine theta equals x, then if we did the inverse, which is the inverse hyperbolic, so when we look for the inverse function, we're looking, I give you a number, you tell me the angle it came from. So since we're integrating for the d theta, this is the angle. So now we got to find out what c is. So to find c, set x equal to 0. So we have 0 at 0. So we have a squared over a, that's just 1 plus 0. ln of 1 is 0, so c is equal to 0. So our inverse hyperbolic sine function, since c is equal to 0, it simply becomes the function. And that's all we have to do. Oh, we do have, okay. That one wasn't looking for a number, it was looking just how it relates. Because we are integrating for d theta, it's in essence, we're looking for the what the reference angle is. Here we have example 3. Evaluate x squared over 9 minus x squared. The integral of x squared dx over the square root of 9 minus x squared. So here we're looking at a squared minus x squared. So a squared is 9, so a is 3. Now from our first equation, a squared minus x squared, we'll be using x equals a sine. So we know that x is equal to 3 sine theta. So dx would be the derivative of sine is cosine. So we have 9 minus x squared. 9 minus x is 3 sine. Squared. Distribute, so we get 3 squared is 9 sine squared theta. 1 minus sine squared theta. 9 cosine squared theta. Again, the reason we do this whole part, because now when we plug it back into the radical, this square root of 9 is 3. Square root of cosine squared is cosine. So this whole denominator becomes that. So we get, so our integral of x squared dx, 9 minus x squared, becomes the integral and we're only dealing with positive realm, so we take the cosine absolute value of it. Dx is 3 cosine d theta. So that's what dx is. So x squared would be 3 sine theta squared dx. There's x, 3 sine. Here's dx, so it's 3 cosine d theta. Distribute that, so we get 9 sine squared theta times 3 cosine theta divided by theta all over absolute value of 3 cosine theta. This is d theta. Okay. Those cancel. The constant goes in front. Yeah, and let's look at back at our domains. For sine, we're looking at negative pi over 2, pi over 2. All right, so we have 9. The integral of sine squared. Looking at our cheat sheet, we can't do squares, so we write it as 1 minus cosine 2 theta over 2. Two comes out in front, it's a constant. 1 minus cosine 2 theta d theta. So we have 1 minus cosine 2 theta d theta. Integral of 1 is theta. Integral of cosine is sine over 2. Plus our constant. We can simplify it by double angles. We know that sine 2 theta is equal to 2 sine theta cosine theta. Because we don't want exponents, and if we could get rid of the double angles back into regular angles, we'll do much better. So we get theta minus 2 sine theta cosine theta over 2 plus c, the 2's cancel. All right. Now we have to convert. We have to find what theta means, what sine theta equals, and what cosine theta equals. So here's, we can find theta here. So we know that x is equal to 3 sine theta divided by 3. And then take the inverse of both sides. So theta is equal to the inverse of sine x over 3. And sine so sine theta is simply x over 3. And cosine cosine squared. So we figure out what cosine is from that. So 9 minus x squared equals 9 cosine. So I subtract 9 from both sides. No, not subtract. I have to divide by it. Because it's multiplied to it. Now I square root the top and the bottom. So cosine theta equals 9 minus x squared over 3. So I have that. I have that, and I have that. So our integral of x squared dx 9 minus x squared becomes 9/2. Theta is the inverse of sine x/3. Sine is x/3. Cosine is 9 minus x squared over 3 plus c. That this times this. Minus x over 9 square root of 9 minus x squared plus c, and distribute. 9/2 inverse sine x/3 minus 9/2 times 9 is simply x. 9 minus x squared over 2 plus c. So 9/2 inverse sine x/3 minus x times 9 minus x squared over 2 plus c. And one more. Evaluate this one. 25x squared minus 4, where x is greater than 2/5. Evaluate. Dx 25x squared minus 4, where x is greater than 2/5. None of our formulas have a coefficient, so we have to get rid of the coefficient. Conversion functions in front of x, we need to remove it. So if we factor out a 25, remember, when we factor something out, to figure out what goes inside the parenthesis, you divide. So that we have x squared minus 4/25. So square root of 25 is 5. X squared. The square root of 4 is 2 over 5 squared, which is why we said that x has to be greater than 2/5, because if it equals 2/5, then we got a 0, and we can't have it on the bottom. So it's got to be greater than 2/5. So A is equal to 2/5. And so what we have, we use this function, x squared minus a, that's the secant function. X squared minus a squared, that's the secant function. We use x equals a secant theta, which is equal to 2/5 secant theta. We find dx equals 2/5. The derivative of secant is secant tangent. And our domain is because we're only dealing with the positive side, and tangent has an asymptote at pi/2. This gives us x squared minus a squared equals x squared minus 2/5 squared. Is equal to x is 2/5 secant theta squared minus 2/5 squared. Four over 25 secant squared theta minus 4/25. Factor it out. We get secant squared theta minus 1. Secant minus 1 is tangent squared theta. So we know that x squared minus a squared is 4/25 tangent squared theta. So the square root of x squared minus a squared equals the square root of 4/25 tangent squared theta. 2/5 tangent theta. And again, tangent's always going to be positive. It has to be positive. So we're looking at It's our original equation. In our original function. So our original equation was dx square root of 25x squared minus 4. First thing we did, we got rid of that coefficient. Dx. Our dx is 2/5 secant tangent. In the bottom, this part became that. 2/5 tangent theta. Okay, so the 5's cancel there. The 2's cancel, so we have 1/5. Tangents cancel. Which is equal to 1/5. Is equal to 1/5 integral of secant . 'Now substitute back to our numbers. So let's see what we have. We have secant here, so let's go. We have x equals 2/5 secant theta. Then we have to get tangent. And x squared minus a squared, which was x squared minus 2/5 squared, became two-fifths tangent. So this is the original. So our original function which becomes 1/5. Secant is equal to 5x/2. Yes, secant from this first one. And tangent is 5/2 times x² minus 4/25. Five over two square root of x² minus 4/25. That gives back to our original equation. Oh yeah, because that became part of that. 25 x² minus 4. This is what we did earlier. And when we factor out the 25, it was a coefficient. Yeah. So that's our final answer. Oh, no, that does it for that section.